We left off having motivated the notion that we want to define our muscle lengths as functions of the angles of the joints spanned by those muscles, so that we can determine related expressions for muscle moment arms as functions of joint angles. And this will allow us to then include our Hill muscle models in our models state equations here, and from them compute muscle forces, and with the moment arms, transform those muscle forces into the joint moments that will rotate the joints of the model. So let's define actual expressions here for these muscle lengths so that we can actually do this in practice. To do that, we will need some data. We will need some data to inform us of how exactly muscle length changes with changes in joint angles. And we will again use our OpenSim model for this. So let's load up OpenSim. And let's load up our full body model. And I put this model on the course website for you guys. And here is my model. And to get some data for muscle length as a function of joint angle, I'm going to use OpenSim's plot tool here. And I want it to tell me some muscle tendon lengths. And I want it to do this for two muscles. I want it for glute max R2, or sorry, glute max 2R. And I also want it for vas lat R. Okay. And I want you to tell me the lengths of those muscles as a function of hip flexion. And then I click add. Okay, here I got two curves on one graph. The blue one is the length of the knee muscle, the vasti muscle, as a function of hip flexion. And the red one is the length of the glutei muscle as a function of hip flexion. The blue one's flat, meaning the vasti length does not change with hip flexion, and that's what we would expect. The vasti doesn't cross the hip joint, so its length shouldn't depend on hip angle. The glutei muscle, the red one, does cross the hip joint, and we would expect its length to change as we change the hip flexion. In particular, since it's on the back of the hip joint, we would expect it to get longer and longer here as we flex the hip further and further. So this is just showing what we would expect here data-wise between the muscle lengths and the hip flexion angle here. Data-wise, in terms of data, let's get these data out of here so that we can use them to build some expressions in our own model. So if I right-click here and go to export, I can export these data shown in this graph here. And I'm just going to put this on my desktop here. And let's call it hip muscle lengths.sto. And then I'll delete that curve and change my x quantity here to my knee angle and add it. And here I get the vasti muscle length increasing with knee flexion and nothing happening to the hip muscle. And so let's export those data too. Knee muscle lengths.sto. Okay, if I look at those data files, they look like this. They've got some header information. They've got some column headers, and then they've got four columns of numbers. Time here is really just frame numbers. There's no time or dynamics in these data. The second column is the angle of the hip in degrees. Third column is the length of the glutei muscle. Fourth column is the length of the vasti muscle. Let's get those data into MATLAB. Let's first tell it where they are. And let's load my hip data in here. Sometimes MATLAB's import data here or import data function works real well, sometimes not so well. We'll see how it works here for my hip. And let's put this in my MATLAB folder. I'll just call it muslength.m. And no noises, so hopefully it was happy here. And there is my hip data. Import data here loads in that whole file and splits it up into the different parts that it recognized. So it grabbed my data there, and then it also probably grabbed my header information, which I don't really need, and then my column headers here, which I also don't really need, but it can remind me what's in each one of these columns in my data if I forgot or if I need that information for whatever reason. And let's do the same thing for my knee data. I think my thing here is telling me I don't need those brackets. Let's do the same thing here for my knee data and get those in there as well. So I'm going to load data. And let's then label my variables. I want to pull off my length of my gluteus muscle. That's going to be hip data. And then the data field inside of there. And I believe it was specifically column 3 in those data. And then same thing for my knee muscle, my vasti muscle. That was column 4 in those data. And those should both be changing. And they are. Okay, labeled them right. And just to remind me what I'm working with here, this is my gluteus muscle length versus hip angle. This is my vasti muscle length versus knee angle. Okay, then I want my angle data there. For both my hip and my knee. Okay, before we can move on here, we need to make sure that our angles here have the same definitions in our OpenSim model, where these data came from, and in our musculoskeletal model that we're making, that we will be using these data in, or more specifically, that we'll be using the functions that we define from these data in. So let's remind ourselves of what's going on with our model. I'm going to turn off gravity here for a second and make time real short. And let's just put our model in its neutral up and down pose here. Oh, that's wrong. Undefined. Oh, let's go to there. And comment you guys out. And let's just reset them to 0 for now. Okay. So here's my model standing straight up and down. When I give my model a positive hip angle, and let's just set a small knee angle here so we can visualize this a little better. When I give it a positive hip angle, that flexes my hip. And when I give it a negative hip angle, that extends my hip. Okay. So when it's a positive angle, I want that to move the hip in this direction. And when it's a negative angle, I want that to move the hip in that direction. So let's check in our OpenSim model and see if that's the same or not. So I'm going to view it from the side and zoom in a little. And let's set my hip angle to 0. It's already at 0. When I increase that hip angle, that flexes the hip. And when I decrease that hip angle and into negative angles here, that extends the hip. Okay. So I'm good here with the hip joint between my model where my length data come from and between my model where I'm going to use those data in my MATLAB musculoskeletal model here. So we don't need to do anything to our hip data here in this model. For the knee in our model, let's give it a small knee angle or hip angle here to visualize this. You can see when I give it a negative knee angle, that flexes the knee. And the knee can't extend by too much beyond 0, so let's just give it a small positive angle here. And when I have a positive knee angle, that's knee extension, that extends the knee. Now, in my OpenSim model, there's an inconsistency there. When I flex the knee here, that's associated with the positive direction in the OpenSim model. But in my model, knee flexion is the negative direction. So in OpenSim, this is a positive 90-degree angle, and in my model, I want to call that a negative 90-degree angle. So that's an easy fix. I just need to take all my OpenSim knee angles and multiply them by -1. And remember here in our model, we're working with angles in radians, and these data from OpenSim were in degrees. So let's convert them to radians. Okay, so we're all set with our length data and with our joint angle data. Okay, one easy way to generate muscle length functions as functions of joint angles when you have data for those things is to fit a polynomial to them. And polynomials are a good choice here because the polynomials that we fit will be nice and smooth continuous functions, meaning we'll be able to define their partial derivatives with respect to those joint angles, and also from the virtual work method from the last lecture get our expressions for moment arms as a function of the joint angles. So that's motivating the use of polynomials here, and it also turned out that fairly low order polynomials, fairly simple polynomial expressions, can generally give you good fits to muscle length angle data most of the time. So let's generate a set of polynomial coefficients for our hip glutei muscle length versus our hip angle, and that's with the MATLAB polyfit function. And this is an easy function to use. You tell it the x data that you want to fit the polynomial to. For us, that's Q4. You tell it the y data. For us, that's length of the glutei. And then you tell it the order of the polynomial, some integer greater than or equal to 1. So let's just start with the lowest one, 1. And then we will do the same thing for our knee angle and our knee muscle length, and same minimal order there. Okay. We then want to evaluate our polynomials. So these will be our estimated muscle lengths per these polynomial fits. And that's the polyval function, where you tell it the polynomial coefficients, and then you tell it the angles that you want to evaluate those polynomials over. Let's just label these things so you guys can hopefully be clear what I'm doing here. Estimate glutei length from above. Oops. And same thing for vasti length. Okay, so here I have my actual length of my muscles from my OpenSim model, and then down here I have my estimated length from fitting polynomials to those models. And so let's compare those lengths in a figure here. I'll plot my actual length and black. And my estimated length and a red dotted line. And I'll do that for both of my muscles here. And looks like I forgot a capital. And then let's stick a legend on this first one. And give it some labels. Hip angle. And these are in radians, and we're usually more familiar with visualizing them in degrees, so let's convert to degrees here. Okay, and let's see what our polynomial fit looks like here. Okay, so remember here, the black data are the actual, I think I did this backwards. Yep. Sorry, should be angle versus length. Not length versus angle. Sorry about that. That should look a little better. There we go. Okay, so on the top is showing gluteus muscle length as a function of the hip angle, and on the bottom showing vasti muscle length as a function of the knee angle. In both of these plots, the actual muscle length from the OpenSim model is in black, and the estimated muscle length from the polynomial fit to those data is in red. And you can see here when we fit a first order polynomial, which is just fitting a straight line to those black data, they don't fit it very well. Now let's use a higher order polynomial here. Let's allow a quadratic fit there with a second order polynomial. And we can see there we fit a little better. We're pretty much spot on there with gluteus. Still some small deviations there with vasti. So let's try a third order polynomial. And still pretty spot on with gluteus. And a little bit better with vasti. Still some small deviations there at the extreme angles there. Let's try 4. And with fourth order, we're pretty spot on with both of them there for both the gluteus length and the vasti length. In general, as you increase the order of the polynomial here, you're fitting a polynomial with more and more free parameters to those data. So what I just showed you there by increasing the order of the fit and getting it to fit the data well there is not remarkable in any way. That necessarily has to happen. It's having more free parameters to fuss around with the parameter values and fit that red line to those black lines as well as it possibly can. In general, you don't want to just make this some arbitrarily high value, like don't just make it 20 and fit the data super well. In general, you want to make this order of this polynomial fit as low as you possibly can while still fitting the data well. Normally, you'll see fits here on the order of like 2 to 3. You don't see a lot of fourth order fits, and so we're going to go with just cubic fits here. And just live with the fact that we don't fit the vasti length quite as well as we did for the gluteus length here. But these deviations are pretty small here. These are on the order of less than a centimeter, or so well under a centimeter here, deviations in the fit there. So we'll go ahead and use third order polynomials here. Okay, if I look in those p vectors that MATLAB created when I did my polynomial fit. This is the p1 created for the gluteus muscle. It's a vector of 4 numbers here, and what are those numbers? These are the polynomial coefficients that I would use to define my actual expression for the gluteus length as a function of the hip joint angle. And so that expression would look something like this. I would have my gluteus length would be the last term in that vector of p-values. Sorry, that's p1. Plus the next to last term times the angle plus the next to last term times the angle squared plus the first term times that angle cubed. Okay. And similarly, for my vasti muscle, whose coefficients are in that P2 vector, that's what that muscle's polynomial looks like there. Okay. Now, these p-values here, these are all constants, and so their values aren't changing as a function of these joint angles here. So I can take the derivatives of these functions here to get expressions for the moment arms. This first one here would be negative dl1 over dq4. And this second one, r2, would be negative dl2 over dq5. Now, for simple expressions like this, these are pretty easy to do by hand. In MATLAB, suppose you have some uber complex polynomial here. You can use, what do I want to call these? K, maybe? You can use this poly-dir function to automatically determine the polynomial's coefficients associated with, should be P1, associated with the derivatives of that expression. Analytically here, where did my, wrong one, sorry. Analytically here, my R1 would be derivative of that constant with respect to Q4 is 0. Derivative of this term with respect to Q4 is P1, 3. Derivative of this term with respect to Q4 is 2 times second coefficient times Q4. And then derivative of this last term here would be 3 times first coefficient times Q4 squared. So no need to put the 0 in there. And then we would end up with a similar looking thing here for moment arm of the other muscle there. Okay, so something to note here is that the order of your fit that you do here for your polynomial function of length, whether it's a first order, second order, third order, fourth order polynomial, also is going to determine the order of your moment arms here. So specifically, you lose 1 order of complexity there in your polynomial with every derivative that you take here. So if it's a third order polynomial function of length, your moment arms are going to end up being second order polynomials. This is why I and a lot of people that use this method like to do third order fits here. They're typically complicated enough to give you decent fits to the actual data while also being low dimensional enough to also still give you the moment arms as nonlinear functions of these angles here. If I had done second order fits here for my length data, then my moment arms would be first order fits, meaning my moment arms would be linear functions of my joint angles, which isn't necessarily always the case. There's no reason to necessarily assume that they're linear. If I had done first order fits to my muscle lengths here, if I just made them linear functions of my joint angles, then that would be equivalent to assuming that my moment arms are constant and that they don't change as the joint angles change. For some muscles in some planes of motion, that's actually not a bad assumption, just assuming the moment arm is constant, especially in the sagittal plane, in the lower limb, over fairly small ranges of motion. Assuming that moment arms are constant length is generally not a terrible assumption, at least some of the time. But in general, broadly, moment arms are not constant with respect to joint angles and aren't necessarily linear functions of joint angles. And so this is why using cubic polynomials here for the expressions for muscle length is a good idea. It's the lowest order polynomial that will still give you moment arms that are nonlinear functions of the joint angles. Okay, so the actual data that we need out of here is going to be these polynomial values here. So I'm going to copy these values here from my polynomial fits, and I'm going to paste them into my parameters script here for my musculoskeletal model. And I'm going to call these my muscle length polynomial coefficients. I get annoyed here how MATLAB does this in what seems like reverse order to me, where it puts the first coefficient at the end of the vector and then kind of does them right to left. I'd rather have my first coefficient be first in the vector, and so I'm going to rearrange these here. I suspect there's probably a way to automatically do that in MATLAB, but rather than try to figure out what that is, I'm just going to manually copy paste them here. Okay. One thing to note here is that these first polynomial coefficients here, which are typically the largest values of all your coefficients here, these are what you can think of as kind of the neutral length of the muscle. This is the length of the muscle when all of the joint angles have their zero values. And these are important parameters to kind of have a reality check here. Like if you get a value of 20, or sorry, of a 0.2 here, does it seem reasonable that a muscle in the body is on the order of 20 centimeters long? Yeah, that seems pretty reasonable. That seems like a pretty normal muscle length. If you get a value here of like 0.001, do we have any muscles, at least major muscles in the lower limb, that are a millimeter long? No, that doesn't make sense. If you get a value of 100, then do we have muscles that are 100 meters long? No, that's a little too big. And so this is a good check on reality here. This will also be an important parameter to consider when we get into parameterizing our muscle models and assigning values for, say, the optimal length of, optimal CC length of the muscle and unloaded SEC length and those things. Okay, those are all we need for polynomial coefficients for our muscles. And now we can go into our our model function and define the lengths of the muscles, not in kind of nebulous form here, but in actual form. So my length of glutei here is going to be P1 of 1 plus P1 2 times Q4 plus P1 3 times Q4 plus Q1 4 times Q4. And this one will be cubed. And that will be squared. And then similar looking thing here for my vasti muscle, which is a function of Q5. Okay, and where are you unhappy? Value might not be used. That's okay, we haven't used it yet. And then my moment arms are going to be the derivatives of those functions. This one will be 0. This one will just be P2. And then on each term here we lose an order. And don't forget to stick a negative sign on those. Okay, and there we have expressions for our muscle lengths as functions of joint angles and our muscle moment arms as functions of joint angles. Let's stop there, or else this is going to be a really long video, and then we will get into next time implementing our muscle activation and contractile dynamics so that we can at last compute the joint moments acting on our model and actually move our model in response to excitation signals sent to the muscles.